So in today's video, we're going to be talking through atomic structure. We're going to be looking at what makes up our atom, what our subatomic particles are called, what their relative masses and charges are, and what happens if we change the number of a certain subatomic particle. So if we look at a helium atom, then we can say that it has 2 protons, 2 neutrons, and it also has 2 electrons. Now, if we are to label these subatomic particles with their relative masses and charges, then we can say that a proton and a neutron both have a mass of 1. A proton is positive and has a +1 charge. A neutron is neutral, as the name suggests, and an electron has a -1 charge. So the electron is much, much smaller than a proton or a neutron, and therefore has a much lower mass associated with it. So we can say that the mass of an electron is 1/2000. Now, when we're calculating, say, an atomic mass or a molecular mass, we don't take into account the number of electrons. If you have a different number of electrons, it doesn't matter in terms of calculating the mass. Because the mass of an electron is so much smaller than the mass of a proton or a neutron, we don't count it towards the mass when we're adding everything up. So let's pretend for a minute that we can just add another proton onto this. We need to think what that will do to our structure. We've got 3 different things that can change within our nucleus, within our atom, which is our protons, neutrons, or electrons. If we change the number of protons, then we change the atom completely. So when we had 2 protons, we had helium, but now that we've got 3 protons, we've got lithium. We can tell this based on the atomic number that we can see in the element in the periodic table. So if we've got an element X, X is going to have 2 numbers associated with it. It's going to have the number above and the number below. Now, the number above, the bigger number, is the element's mass number. Now, this is the total mass of that atom, of that element. This includes protons and neutrons all added up together. The number below, the smaller number, is our proton number or our atomic number. And as the name suggests, this is going to tell us how many protons we have within that element. So for our helium, we had a total mass of 4 because we had 2 protons and 2 neutrons. And then we had a proton number of 2 because we had 2 protons. Now, anything with 2 protons will always be helium. We can change around the other subatomic particles, neutrons and electrons, and that wouldn't change the element. It would just change either the mass or the charge. But changing the proton number changes the atom completely. So anything with 2 protons is always helium. Anything with 3 protons is always lithium. Now, I've drawn a stable isotope of lithium here because, well, just because that's how it would appear on the periodic table, either as lithium-6 or lithium-7. But obviously, that's not what we have here. We were just pretending we could add a proton to the helium nucleus in this case. So next, while we've got them up on the screen, we'll look at isotopes. So if we were to change this to lithium, we'll add in another proton to make it 3 protons, and then we're going to add some more neutrons also. So you can tell by the mass number and the atomic number how many neutrons a certain isotope of an element has. As we said, the proton number is the number at the bottom, the smaller one. And so we can see for this lithium, we must have 3 protons. So our protons are equal to 3. Our total mass is equal to 6. And so that means that we must also have 3 neutrons inside this lithium. So in this case, our neutrons are also equal to 3. Now, you can see there's no number in the top right here for lithium, and that means the lithium has no charge. So what that means is the total number of protons is equal to the total number of electrons. And so these must also be equal to 3. So that means we need to move up to our next shell of electrons. Now, if you're not confident with electron shells, I'll attach a link to the video on electron shells up at the top, where we'll talk through electronic structure and how to properly assign electronic structure. So this will be going a bit above the GCSE, where you just say like 288, for example, and we'll be talking into the individual orbitals and how we actually fill our orbitals within a shell. So we have our 3 protons, 3 neutrons, and 3 electrons then. If we want to make lithium 7, all we have to do is add 1 neutron. You can see from the lithium, our proton number has stayed the same. So this means that we are still with a lithium atom. Remember, if we change the number of protons, it would change the atom completely. We'd be looking at something else. You can see now that we have a heavier mass. So if our number of protons hasn't changed, it must be the number of neutrons that's changed. So our neutrons now must be equal to 4. You can still see that there's no charge associated with the lithium. So that means that the number of protons must be equal to the number of electrons. And so our number of electrons must also be equal to 3 in this one as well. So you can see that all that's changed is the number of neutrons. So this is what we call different isotopes of the lithium. So we can define isotopes from this, and we can say that isotopes are the same element. So we've got isotopes of an element are atoms with the same number of protons, but a different number of neutrons. So isotopes equals an element with the same number of protons, but a different number of neutrons. So this means that our isotopes therefore have different mass, which is shown obviously by the 6 and the 7. So we have a heavier isotope of lithium with 1 more neutron. Now, obviously, because neutrons are neutral, we've not affected the charge of them at all. This is if we change the number of electrons. So now we'll form an ion of lithium. So if we remove this electron here, we are now missing one of our negative charges. So that means that when we draw this lithium out, we're going to have to draw it as lithium plus. That's because we've still got 3 protons as it's lithium. You can see here we have 4 neutrons, so that makes us up to a total 7 mass. So we're with the lithium 7 isotope. So when we form an ion of this isotope, we have 3 protons, 4 neutrons, and because we have a positive charge, this means we must only have 2 electrons. So 3 protons, 4 neutrons, but our electrons are now only 2. We have lost an electron, and we now have the same number of electrons as a helium atom would. And so we have a full outer shell of electrons. Now, this is what most things will tend to do. They will tend to either form the number of bonds required or lose or gain the number of electrons required to get a full outer shell. This is seen as a more stable electron configuration. And so when things react, we see them react in a way that allows them to get a full outer shell. So in this case, the lithium had one valence electron, so it lost that one valence electron to form a lithium 1+ ion, and therefore have a complete outer shell, the same as the noble gas helium. Now, its other option was to try gain 7 electrons. And as you can probably tell, moving 7 spaces in one direction on the periodic table, gaining 7 electrons to have the same electron configuration as neon, would take way more energy than just losing 1 electron to get the same electron configuration as helium. So if we get a little bit more space, we can see the lithium-7 atom and the lithium-7 ion have the same mass because the electron doesn't weigh very much. They have the same number of protons because they're both lithium, but now they have a different charge because they have a different number of electrons. So we can therefore classify an ion as the same number of protons, the same number of neutrons, but a different number of electrons. So an ion is therefore a charged species. With a different number of electrons, but has the same number of protons and neutrons. So now that we've been through all that, I'll put up some examples of things for you to try. If you want to pause the video once I've drawn them out, then you can try assign the number of protons, neutrons, and electrons for these different species. So if you want to pause it here, have a go at assigning the number of protons, neutrons, and electrons for all this, and then I will go through the answers in just a moment. All right, so now that you've given it a go, we'll go through and we'll assign the number of protons, neutrons, and electrons for all of our different species here. It's good to try go through and say which ones are isotopes of each other, which ones are ions, and which ones are just atoms also, as they can ask you this during the exam. So for our fluorine here, you can see that we've got a proton number of 9, and so our number of protons must be equal to 9. Now our total mass number is 19. So to get the number of neutrons, we're going to take 9 away from 19, so we must have 10 neutrons. Now there's no charge associated with this fluorine, and so our number of electrons must be equal to our number of protons, so there is 9 electrons also. Now with our magnesium, we've got a proton number of 12, so we must have 12 protons. Our mass number is 24, and so if we take 12 away from 24, we're going to have 12 neutrons, sorry. Then our number of electrons must be same as the number of protons because we don't have any charge on the magnesium. There's no number in the top right. And so we must have 12 electrons also. Now, for this sulfur here, you can see we've got a 2- charge. And so we would actually call this sulfide. So the "ide" ending that we see here, it lets us know that we are got a negative charge and that the ion is by itself. By itself, what I mean is that we just have sulfur charged. There's no other things making it a compound ion. So for our sulfur, we have 16 protons because we have a proton number of 16. We must have 16 neutrons because we make up a total mass of 32. And then we have a 2- charge. So what we need to do is think sulfur would normally have 16 protons. Sulfur always has 16 protons. It would normally have 16 electrons to balance out those 16 protons. Now, because it's got a 2- charge, that means that it must have 2 extra electrons. And so it must have a total electron number of 18 now. So you can see the sulfur has gained these 2 electrons so that it then has the same electronic structure as its nearest noble gas. It's now got a complete outer shell. And so it's given itself the same electron configuration as argon. So again, we'll go through all of that in more detail when we go through the electronic structure module, which I linked earlier in the video. So now, when we come to argon, you can see that we have a proton number of 18. And so we must have 18 protons. Our neutrons are going to be equal to our mass number, take away our proton number. And so we must have 22 neutrons in this argon. Now we've got no charge associated with this, so we must have an equal number of protons and electrons. Now for this sulfur here, we don't have a charge. So this is just a sulfur atom, not a sulfur ion like we had before. So our number of protons is still 16 because it's still sulfur. But you can see now that our mass number has changed. So this means that we must have a different isotope of sulfur. So you can see that the sulfur has a 2 units lower mass number. And so that must mean it has 2 neutrons less. So now we only have 14 neutrons. We don't have a charge here, so our number of protons is equal to our number of electrons, so we have 16 electrons. Lastly, our calcium, we have 20 protons. We therefore must have 22 neutrons, and we must have 20 electrons to balance out the number of protons. So next, I'll go through some common ions that certain species form. It's really easy to see what ions something is likely to form based off what group it's in. So we're going to look at the first row of the periodic table and see what ions certain groups are likely to form. So we're going to start with lithium, and you can see lithium is in group 1, and so it will want to lose 1 electron because it's got 1 electron in its outer shell to get to its nearest noble gas. So lithium forms a +1 charge. Beryllium is in group 2, and so we'll want to lose 2 electrons to get to its nearest noble gas, as it has 2 electrons in its outer shell. So this forms a 2+ charge. Now if we go over to nitrogen, nitrogen is in group 5, and so it has 3 electrons to gain to get its octet, so to get to 8 electrons. This is easier than losing 5 electrons going back towards helium as an electronic structure. It's easier for it to move towards neon. And so it's going to gain 3 electrons and form an N3- ion. Now, remember, when we call this ion, we have to name it as nitride because it's negative and it's by itself, just like the sulfide was before. Oxygen is in group 6, so has 2 electrons to gain to get to its nearest noble gas. So it forms an O2 minus ion, known as the oxide ion. And then lastly, we have group 7, which is has 1 electron to gain to get to its nearest noble gas's electronic structure. And so this would be the fluoride ion. So things will tend to move towards their nearest noble gas with the least number of spaces to get to that noble gas. And so that's why beryllium doesn't gain 6 electrons to get to neon. It would rather lose 2 electrons to get to helium. Let's just fill in the rest of these so that you can see what's in between. So we can see then that it's easier to move 2 steps to the left to get to the same electronic structure as the helium, rather than moving 6 spaces to the right to get to neon. So it will do whatever is easiest for it to get to its nearest noble gas electronic structure. So when we have different isotopes, then we can end up with different mass numbers. So what we need to do when we calculate the atomic mass of something is take into account the relative abundance of these isotopes. So we can classify our atomic mass as the weighted mean mass of an atom, of an element, compared with 1/12 of the mass of an atom of carbon-12. So we need to make sure that we are saying weighted mean mass of an atom of an element for the mark there. It's the weighted mean mass because it takes into account all our different isotopes. And then to get the other mark for the definition, you would need to say compared with 1/12 of the mass of an atom of carbon-12, as everything is on this carbon-12 scale. So when we're switching to an isotopic mass definition, it's really easy to switch between them, as all we have to do is say that we are talking about an isotope, an atom of an isotope instead of an atom of an element. So our relative isotopic mass then is the mass of an atom of an isotope compared with 1/12 of an atom of carbon-12. So the way that we work out our AR then, our atomic mass, is using these isotopic abundances. So here we're told that we need to find the relative atomic mass, so our AR, of boron, given that 20% of that boron is equal to 10 as a atomic mass, and 80% of that boron is equal to 11 as an atomic mass. So we have 2 isotopes then. We have boron 10 and we have boron 11. They'll have the same number of protons because they're the same element, but they're going to have a different number of neutrons. So both borons will have the atomic number 5, as they have 5 protons, but they have a different number of neutrons. So the way that we do this is we times by our relative abundances. So we take our mass of 10 and we times it by that 20%. And we're going to add that to the 80% times 11 for the other mass. When we get this out, it should come out at 1080, We then need to divide that by 100 to get rid of those percentages that we had. So we divide that by 100 and we get a mass of 10.8. Now, it's important to bear in mind that these masses aren't always going to come out the same as you get on the periodic table, because we are given experimental data a lot of the times, and there'll be error within this experimental data. So we don't know that it's going to come out exactly like it says on the periodic table. So you can't just put down the mass that you've got on the periodic table and hope for the marks, because they're testing that you can do the process, not that you can get the right mass. So don't be worried as well if your answer comes out as something different than what's on the periodic table. That's completely normal as well. So we can be given mass spectra to work out the relative atomic mass as well. So here we are told that we have a mass spec of lithium, and we are told that we have two isotopes on this. So one of our isotopes is lithium-6 that we saw before, and we've got a relative abundance of 7.6%. And then our other isotope is lithium-7, which is present 92.4%. So this means if we had 100 atoms of lithium, nearly 8 of them would have a mass of 6, and 92 of them would have a mass of 7. So the units for these axes, and this is the percentage abundance of the lithium isotopes. So just an intensity reading. And then, as always, on a mass spectrum, our x-axis is equal to mass divided by charge. Now, for the A level, you will always see a charge of +1. And so you don't have to worry about dividing the mass by anything. It will always be 1. But if you ever get asked for the units, make sure you say mass divided by charge. Sometimes it will be shown as m/z, where obviously m represents our mass and z represents our charge. So we're asked to work out then the atomic mass of lithium. So we can see that our percentages add up to 100. So we can do the exact same method as before. We can say that we've got 7 times 92.4%. And we're going to add that to 6 times 7.6%. So when we do this, just let me grab a calculator. So when we do this, we're going to get 646.8 added to 6 times 7.6, 45.6. So if we add those together and then we make sure that we divide by 100, so we're going to get 692.4, but we need to divide that by 100. So we are going to get a mass out for our lithium of 6.924 for the lithium. So again, this is our weighted mean mass, taking into account the relative abundances of our isotopes. So we also need to be able to do this when we have a abundance greater than 100 as well, because that was a percentage that we saw. It was the percentage abundance, but we can also get a reading from a mass spec where we just have relative abundance. So this is just intensities relative to each other, rather than average, like rather than being set to be a cumulative 100. So here we have a mass spec of neon. And now we have multiple different isotopes that we're reading off. We get told that neon 20 has a relative abundance of 114. Neon 21 has a relative abundance of 0.2. And neon 22 has a relative abundance of 11.2. So we do the same method as we did before. We say that we've got 20 times 114. So even though this is above 100, we still take it as the it's our percentage. So we times it by 114, and we're just going to divide by a new 100%. So whatever our total is what I mean by a new 100%. So we add that to 21 times 0.2. We add that to 22 times 11.2. And this comes out at 2530.6. So then our second step is to add all these up to work out our total. So we do 114 plus 0.2 plus 11.2, which comes out at 125.4. We can then do our 2530.6 divided by 125.4, which comes out at 20.2 as our atomic mass for the neon. So whenever you get presented with something that doesn't add up to 100, you have to divide it by the new total rather than dividing by 100 like we did previously. Okay, so I'm going to leave that there for today, and I'll see you next time when we will go through the electronic structure. All right, thanks for watching. Bye.